Let's now talk about localization. Why do we want to localize the vehicle? Well, in order, for example, to control the vehicle with respect to a path, we require knowledge about the position of the vehicle clearly. Sometimes local knowledge is sufficient, such as when, for example, driving on a highway and we just need to laterally control the vehicle. But often the global location is required. For example, in the context of path planning algorithms that we'll have a look at in lecture number 12. Or also when we want to determine relevant elements that have been marked a priori in the map, such as street signs or lane markings, and we want to take advantage of this knowledge for our self-driving car. There's different approaches to localization. Of course, we can use satellites, but these require infrastructure, and there's some downsides to satellites, which we'll come to. And then there's visual localization, which uses visual maps. This could be either at the image level, so quite coarse. And then we talk about topometric localization. Or there's learning-based localization approaches and feature-based localization approaches as well, similar to the feature-based SLAM methods we were talking about before. And then there's also map-based localization. We can use a raw road map as extracted, for example, from Google Maps or OpenStreetMap, plus relative motion estimates from visual odometry to localize in that roadmap as well. And we're going to talk about all of these approaches in this unit. Let's start with satellite localization. This is something we are all familiar with. The first satellite systems for localization have been deployed by the United States in 1978, starting with 24 satellites, and that system is called GPS. By now, we have 30 satellites in orbit, and since 2000, full accuracy is available to all users, not just to military users. By today, there is also other nations that have launched satellites into orbit. For example, Russia has 24 satellites, and the system is called GLONASS. In Europe, we have the system Galileo with 30 satellites, and China has the system Beidou 2 with 30 satellites. And modern GPS receivers can take advantage of all of these. The more satellites you can see, the more accurate your poses and the more available your pose estimates are. So here's an example where you can see that, of course, not all of the satellites are visible. Visibility depends on the local neighborhood that you are driving in. If you have a skyscraper next to you, you can't see many satellites. But even if you would be on a very open field, you can only see some of the satellites and not all of the satellites, as they are orbiting Earth and they are occluded by Earth itself. And so it's important to see as many satellites as possible to localize as accurately as possible. The principle of localization through satellites is called trilateration. The goal is to determine the location of the device or the vehicle by measuring distances to satellites at known locations using the geometry of circles and spheres. So we know where the satellites are, and we can measure distances to the satellites in order to triangulate our own position. The distance to each satellite is measured hereby as the time delay between the sent signal, or a code in practice, and the received code. The receiver has to know the code, and it does. And as you can imagine, small discrepancies in the time measurement have a tremendous impact on the location, because we're talking at really small time delays here. Satellites are equipped with an onboard atomic clock, and given one satellite, we only know which sphere we are on, because we know the distance to that satellite. Given 2 satellites, we already know which circle we are on, and given 3 satellites, we know the exact location. In practice, a 4th satellite is needed for time synchronization, so you need at minimum 4 satellites to be visible in order to use such a system. The system can be further improved through so-called differential GPS, where there's a set of ground stations at a fixed location, very precisely determined fixed location, and you also use the GPS signal from those locations to correct for atmospheric effects, for example. And this is what, for example, the red box, the GPS combined inertial measurement unit that I've shown before, can do. It can connect to such local ground stations. So how does localization work? Well, we have to measure time delay, and the way this works is that the satellite generates a signal here in blue that is received at a certain time delay due to the distance of the satellite. And as the signal travels with the speed of light, so this is a very short time delay, and then our measurement device, the receiver, knows that signal, and it adds an artificial delay, such a phase delay here, until these 2 signals match, and through that it can calculate the distance to the satellite. Now we're going to do this with respect to all the satellites that are visible to us, to the receiver. And here's a 2D illustration of what happens then. So let's assume the first satellite is measured at this distance, so we know we are on that circle. The second satellite is measured at this distance, so now we have narrowed down the location to these 2 points here. And then if we measure a third distance, then we know exactly where we are. And in 3 dimensions, this looks something like this. One important thing to note here is that it depends very much on the constellation of the satellites with respect to you and with respect to each other. The variance in the estimate can heavily depend on this. So the precision with which you estimate your location is affected by this. Here's an example where we have 2 satellites, but of course you're not 100% sure about the distance to the satellite because of measurement noise, and so the only thing you know is that you're within these 2 circles here, the 2 gray circles. So you don't know that you're here at this exact location, but you know that you're somewhere here in this green region because you're within these uncertainty bounds. Now, if the satellites are located like this is a nice situation because we have still confined the uncertainty region to a relatively small area. But if the satellites would be located like this, then you can see that this green region is much larger. And this is what in satellite navigation systems is called geometric dilution of precision, or GDOP. It's a value that can be calculated that tells you how accurate your pose estimate is. So these pose estimates, the quality of these pose estimates ranges in the order of 1 to 5 meters, and it can be reduced by using additional accumulation through inertial and fusion with inertial measurement unit measurements, as well as differential GPS, up to a few centimeters in very idealistic conditions. However, so this sounds all very nice, right? But there's some problems with satellite localization. The first is availability. Satellites are, for example, they are not visible in tunnels or narrow city streets because there's too much shadowing, too much occlusion. And their availability also depends on national organizations or interests. The accuracy depends. It is in the order of a few meters for raw GPS and in the order of a few centimeters to meters for differential GPS, depending on where you are in very open conditions. And if you combine this with an inertial measurement unit, you can get precision up to a few centimeters, but this is happening very rarely. Maybe you can use this on open sea, but not for driving. Also, we are receiving only the location of the device, not the rotation. So there's no full pose measured unless we fuse this information with, for example, information from an IMU. The frequency is also a problem. The frequency is maximally 5 to 10 Hertz, so we don't get location estimates more frequent than that, which is of course needed if we want to, for example, control a vehicle. Then this has to happen at maybe 500 or 1000 Hertz. So the measurements that we are receiving are too sparse temporally to directly do that. And then there's atmospheric variations, which lead to errors in the time measurements, but this can be partially corrected by differential GPS using signals from nearby base stations. However, the GPS requires communication and initialization, and it requires these base stations to be built in the first place, and depends on the availability of them. So there's a lot of factors that need to be satisfied here as well. And then finally, there is something called multipath effects, which is if you're driving in a narrow city street and there's a building next to you, then the signal from the satellite might reach you directly, but it might also reach you through a reflection on the facade of that building. And that means that the time that you measure is actually wrong, because it's not the direct connection, the direct line of sight to the satellite that you're measuring, but this indirection through the building facade. And so through this you get errors in your estimate, which have to be filtered. But sometimes it's really hard for the system to filter these errors if there's too many of these multipath effects going on, and then the signal can jump around. And this is illustrated here in this little presentation or demo from Danny Irland, who is an engineer at Uber. Uber, the company that provides a car sharing or taxi service, of course, needs also very accurate localization of their vehicles. And so here's a little demo what happens if you try to use GPS in urban environments.
So there's a big problem with GPS. When you're surrounded by tall buildings, the reflections and multipath fading, basically the signals go all over the place. So in this example of leaving Uber HQ, as soon as you get outside, the GPS goes like 100-meter error, across a whole city block.
Yes. Okay, so this illustrates a little bit how difficult it can be to use GPS, or if one would rely on GPS alone for self-driving, that wouldn't be a good idea. It doesn't work. That's why we need other techniques for localizing, and one is visual localization, which we will talk about now. The main idea here is to record a map or database of known locations with associated features. The map could be a collection of 3D landmarks with feature vectors that describe the appearance of the landmarks. The features can be extracted, for example, from images or laser scans as part of the map building, for example, in the context of SLAM. Mapping should, of course, be conducted under similar conditions as during localization to minimize domain shift with respect to the sensor setup or environmental conditions. So you'd like to use, first of all, you want to map what is of interest to you at test time, and then you want to map it using the same sensors. At localization time, we then try to retrieve features extracted from the current input, image or scan, and we want to retrieve those again in the database to localize. We can localize only at the image level. That is what we'll call topometric localization. Or we can refine the pose more precisely to yield an exact pose, 60 pose estimate using triangulation or geometric pose estimation. There's many challenges involved in the localization problem. The first is, of course, that the map can be quite big, so we need to very efficiently, in real time, retrieve the correct information within a very large database, and that's challenging. And we'll talk about this later. But another challenge is also that if you use, for example, image sensors, the appearance and also the geometry of the scene can change dramatically. So here's some examples from the Oxford Robocar dataset. This is a dataset that has been created by one car driving always the same routes over the course of 1 or multiple years even. And you can see that here in red, sometimes the geometry can change. For example, the tree, they lose their leaves in the winter. But also the appearance can change dramatically. In this case, where you have sunlight coming from the front, or you have a cloudy day where the weather is the light is more diffuse. Then you have shadows if there is sunlight, or at night the scene looks completely different. Now, if you want to localize a day image versus a night image, then of course you need to take into account these appearance changes as well. The first technique that we will look into is called topometric localization. And this is a image level localization technique, which means that we only localize with respect to a frame ID. We don't retrieve the 60 pose, just a frame index. This is something that has been proposed by a team from CMU in a paper called Real-Time Topometric Localization at ICRA 2012. The setup is as follows. We record a sequence with cameras, LiDAR and GPS as ground truth are used. And then we want to localize a new image from a different day or season with respect to the recorded sequence. We want to retrieve the image from the recorded sequence that's most similar to the image that we currently observe. And it's called topometric because it combines metric and topological localization. Metric in the sense that we optimize the pose with respect to feature correspondences, which we don't do here. We only optimize for the image, but we use features. And topological because we estimate the observer location qualitatively from a set of finite locations. So it's kind of in between metric and topologic. So what we do effectively is we describe the entire image with a global feature vector and then try to find that feature vector in the database. So we only localize with respect to a particular node in that graph, where each node in that graph is a frame, and don't get the full 60 pose. For map creation, the authors of this project considered the map as a directed graph where nodes are individual frames in that graph, and they are created based on a distance threshold, so that like if the vehicle stands still, no additional nodes in the graph are created which are unnecessary. And then the features that are used are standard surf descriptors, but in this case not applied to local features but to the whole image, yielding a 64-dimensional feature descriptor for the entire image. And then they used a Bayesian localization approach. This is a standard filtering, the standard filtering equations that I show here, which will go into more detail in later lectures. But it's a very standard formalism for updating state distributions. So it can be understood as follows. What we want to model is the distribution over the location, over the graph nodes, where each node is a frame in the map. And we do this by predicting, well, by taking the distribution, let's say we're at time t, then we take the distribution over the locations at time t-1, and then we multiply this with a motion model, which models the distribution of the location at time t with respect to t-1. And then this is the prediction step. And then the update step takes that probability here and multiplies that with the observation probability at time t in order to arrive at the posterior which is here on the left. And then the posterior is again the same expression as this one here for the next time step. And so we can iteratively update this filter equations here. So this is a very common framework. It's also, for example, the framework that the Kalman filter uses. But in this case, it's on discrete locations. So it's a discrete filter, a discrete Bayesian filter. So far about filters, more in the next lectures. In this particular case, what they used as a motion model is a very simple constant velocity motion model. So we take the previous position and then we add some constant velocity and times the time difference in order to get the distribution with respect to the new position. And then there's a measurement model that relates the observation CT with respect to the map features D of xt. Now, strictly speaking, this formulation handles tracking. It's ego tracking, but it can be understood as frame level localization, of course, right? So the question is, what is localization? Here in this case, you need to start at a particular point in time, and you need to know the starting position in order to track yourself through the route. But some localization techniques that we'll also talk about later, they don't make this assumption. There, you really localize with respect to a map without any a priori assumption. But of course, if you know where you are, where you're starting, then localization becomes much easier because it's effectively tracking. And this is what I mean with this remark here. We are effectively talking about a tracking method here. But of course, it's providing a localization to us. How does this look like? This is the results that are obtained. And you can see for both the left and the right image, you see the input images and at the top, and the images from the database that have been retrieved from the database at the bottom. And you can see that the appearance is quite different on these 2 days, but the images have been retrieved correctly. Again, this is frame level localization. We don't have the exact 3D pose. We just retrieve the frame ID. Now, the next part of this unit is on learning-based localization. We can also use neural networks to try to directly regress to the pose, and that is what has been done in PoseNet from ICCV 2015. In PoseNet, what they did is they used as an input an RGB image, and they tried to directly regress the 6 degrees of freedom of the camera pose. That is, the 3D camera position and the 3D camera rotation, in this case represented by a quaternion. And they used a 23-layer deep ConvNet for this based on the GoogleNet architecture, which was popular at the time. It turns out that such an approach is or can be quite robust, more robust at least to correspondence outliers and errors compared to feature-based methods, but it's in general hard to get very accurate results. So it's in general less accurate. So here you can see the loss function and an example at the bottom where the green are the training poses, the red are the predicted poses, and the blue are the ground truth poses. And you can see that the red and the blue don't perfectly coincide, but they roughly match. And this is also visible here, where the outline of the building has been reprojected onto the images used for localization, and you can see that the poses are not perfectly aligned. There's a slight discrepancy, but it's able to recognize which place it's looking at. Okay, now the next localization technique that we're going to look at is feature-based localization. And that's very similar to the SLAM methods that we talked about already. In feature-based localization, the goal is to first create a database, a map using, for example, SLAM techniques, where each of these points is associated with a feature vector, let's say a sift or a deep descriptor. And then we also extract these descriptors from the current query image, and then we match these descriptors to the database descriptors. And once we found matches, we can do something that's called geometric verification. There's going to be a lot of erroneous matches because we are not querying just a single, the most recent image here, like in visual odometry, but we are querying an entire map. So querying millions and billions of feature vectors, and there will be some feature vectors that look similar, but that are at completely different places. So it's important to verify which of these correspondences are actually correct. And then we can, only using the correct correspondences, localize with respect to that map that has been created. So let's go through this step by step. The first step is, of course, mapping. So we want to obtain a sparse 3D reconstruction based on sparse feature correspondences, and we can use the SLAM techniques that we've discussed in the second unit for doing so. Then we associate each 3D point with a local image descriptor, like a SIFT or SURF descriptor. And these descriptors are simply the descriptors that are extracted for these 3D points when they are projected back into some of the images, right? So, like when you run the SLAM algorithm, typically you already have these features because you need them already there to establish correspondences. So you just need to store them. It can also be an advantage to use semantic features to first convert the appearance into semantics, because you can get a little bit more invariant to, for example, the appearance variations that we've seen before, day versus night, winter versus summer, etc. So this turns out to be also helpful to design these features well. Now, once you have extracted features for both the map and your query image, you need to find the features from the query image in the map. And of course, it would be very wasteful to brute force go through all the features in the map. So what is happening typically is using a very efficient search algorithm. For example, we can use an approximate search algorithm like a KD tree or an inverted index that finds these features much more efficiently because of the data structure that it's using. And there's good software packages available for this that are open source and that you can use, like Flan and Feis and so on. And so this allows you to retrieve the nearest neighbors only approximately, but relatively quickly. Now, the next thing you need to do is you need to localize with respect to the retrieved feature correspondences. In contrast to the SLAM problem before, where you have retrieved 2D to 2D correspondences, here we have 3D to 2D correspondences, right? We have the features in the image and the corresponding points in the map. So we need to now find the rigid body transformation such that this image, when projecting the 3D points, the corresponding ones, into the image, then the reprojection error to these 2D observations is minimized. Yeah. So we have a 2D to 3D correspondence as input, and now we need to compute poses, R and T, such that this projection here, the projection error is minimized. And there's very efficient methods for doing so. For example, the PNP method, which is a closed form solution to this problem. And even if you would optimize for this, you can get very efficient solutions because it's a simple optimization problem. Sorry. Now, one big problem here is that because we have so big maps such big maps, and because there's so many features in the maps, and also because we have to use approximate search algorithms for efficiency, a lot of the correspondences that we're going to find are actually going to be wrong. In some cases, more than 50%, more than 80% of the correspondences are going to be wrong. So we can't directly use this algorithm here. But what we need to do is we need to geometrically verify which of the correspondences are correct and which are wrong. So the problem is wrong feature matches corrupt the pose estimation results, and the solution to this is to solve a minimal problem many times and return the best solution. So instead of taking all the maybe 1,000 feature correspondences, we just take 3, because 3 is the minimal set to estimate the 6 pose parameters. Why is that? Well, for each correspondence we have an x and a y coordinate, so 3 times 2, which is 6 observations, and we have 6 unknowns. So this 3 observations are enough. And so we randomly sample these from the features that we found in the image and fit this model, which is very fast, 2 microseconds. And then we search for all the other correspondences, how well they are matching with their respective, how well the other landmarks align with the respective 2D correspondences. And we can count how often they align very well. And then we take the solution that where the majority of the others align. And then we consider this set where we consider all of the ones that project precisely onto the 2D observations as the inliers, and we can do a final optimization step of those only. And then we have rejected all the outliers, all the ones that are incorrect. And that's what Ransack is doing. So here's a pseudo algorithm of Ransack, which says, while the probability of a missing correct model, so there's some probability considerations you can do here, how often you have to do this loop. We estimate the model from just 3 random features, because there's the minimal set. And then we estimate the support, which is the number of inliers, by projecting all the others and see how well those match. And if we have a new best model, then we perform a local optimization and update the best model, and then we return the model with the most inliers in the end. So this is a very effective way of rejecting outliers, and this is responsible for making these methods work, really. These methods really face the problem of having sometimes more than 80% outliers, but using such techniques you can still make it work. Okay, and finally, I want to briefly talk about map-based localization. Just one slide. More details are in this paper here. The idea of map-based localization is to update a location probability distribution that is defined on a map, a road map, a simple road map that can be downloaded for free from OpenStreetMap. And we update this using visual odometry measurements. So whenever, like, we start with a uniform distribution, and whenever we take a turn, there's some information coming in. So we know that at all the locations where no turn can happen, the probability of the location must be reduced. But at locations where the particular turn, like let's say a right turn, can happen, the probability increases. And over time, we localize. Using this technique, we can localize within maybe 30 or 40 seconds in very large maps without knowing anything about our initial location. So it's not a tracking method, it really is a full localization method. I want to show you quickly how that works. So the input is just a map and a monocular video sequence from which we compute visual odometry, and this is used as the observations in a probabilistic filter that updates the distribution of location on that is defined on that map. And so here you can see in the beginning the probability is quite uniform because we haven't made a lot of informative measurements yet, but now we're taking a right turn, and so we know already now that we have to be somewhere right after a right turn, and then after the second turn the particular constellation of relative poses is so unique that we have already localized in this little map here. The nice thing about this is, of course, that you don't need to map the environment a priori, but you can just use a roadmap. You need to know just roughly where you are, and then you can localize in that roadmap. But of course, you don't know the exact 6 degree of freedom pose. You just know where you are along that roadmap. It also works for larger scenes. So here's results on really large maps, and even there, and even on scenarios like this, where there's basically just highway driving, localization happens pretty quickly. Now there's a lot of uncertainty here in longitudinal direction because highway driving is fast and so it's uncertain, but now once we take a turn, it's getting reduced. And here's another example where localization happens after 30 or 40 seconds of driving time. To summarize, today we've seen that visual odometry is a class of algorithms for estimating relative ego motion from images. We've also seen that SLAM algorithms build a map and simultaneously localize in that map. Further, a key feature of many SLAM algorithms is to use loop closure detection to close loops and generate a more consistent map. Localization methods then can use these maps to find the global pose in such maps, but there's different localization methods. Some use maps, some use road maps, some use GPS, etc. We've also seen that indirect and direct visual or odometry or SLAM algorithms can be distinguished. Indirect methods are faster and converge better, but are in general less accurate. In contrast, direct methods are slower, but lead to more accurate results. And direct and indirect methods can be advantageously combined. Except for offline mapping, real-time computation is really crucial because the information about the ego motion or the location has to be available immediately for the following decision-making steps of the pipeline in a self-driving vehicle. That's all for today. Thank you.